Okay, yeah, thanks for being here. I will tell you new tales of wireless input devices. Well, mostly because we did some research back in 2016, and this is an updated research on basically the same topic. As he was kind enough to introduce me, I'm Gerhard Klostermeier. I'm basically a pen tester, analyzing products for security, and as I'm in the hardware department, I'm really interested in all the embedded stuff, radio security, and all that comes with it. This is my dear colleague who cannot be with me here for today, unfortunately. But all these, whenever I talk about we, this is a group effort. So he did huge parts of the research with me. So I want to tell you about a little bit of the introduction, what we analyzed and what devices we used to analyze it, the previous work of other researchers who had a look into the same area. Then I will give you an overview of our research, what we did, the found security issues we detected during the research. I will try some live demos. Hopefully they work. Some conclusion and recommendations. If we have some time, there are 2 interesting anecdotes to tell, really short ones, and at the end, a Q&A session if you have any questions. So let's get started. When I'm talking about wireless input devices, I basically mean the things you can see on this slide. So keyboards, mice is the most common one, but also the presenters, like the keynote speaker used before me. You can talk more freely and use your clicker to switch to the next slide. They are also considered wireless input devices. And the devices we use for analyzing them and attacking them are basically software-defined radios. Well, we use them for at least parts of our research, like the HackerF1. For those who don't know software-defined radios, this is just a generic USB device I can plug in, and I can tell, like the name says, software-defined radio, I can tell in software on my PC how this device should act on the RF spectrum, how it should decode signals, how it should send signals. There are other devices like the Crazy Radio. This is just a really useful tool because there's a chip on it that is the same chip like in at least a lot of keyboards we analyzed. So it's easier to use the same hardware like that is in the keyboard because all the decoding is already in the chip and you have to do that manually. And you even can use the Logitech unifying receiver because it has the same chip as well, and it's reprogrammable over USB. So previous work of other researchers, the interesting ones are like the Key project. Interesting in that case, for example, is the year. It's 2010. So researching wireless input devices is, really old at that point, like close to 10 years. And we have now 2019 and their devices are still not really secure. Also, to give you a quick overview, so this evolved, so the keyboards evolved. The Key project was like for keyboards sometimes working on the 27 megahertz. Nowadays it's all 2.4 gigahertz spectrum. And when I talk new tales of wireless input devices, in 2016 we published some research about secure keyboards. Well, they weren't so secure there. And this is the follow-up project to this. And interesting enough, Mark Newlin, maybe you know him from the mouse jack attack. He did research in 2019 as well on presentation clickers, as well as we, but on other models. So it's interesting to see the differences. And Marcus Mengs, you may saw his tweets or something. He had a closer look at all the Logitech products. So in this project, we want to answer the open questions we had from our last project, and we want to have a closer look in wireless presenters because we didn't have a closer look there. The first research project was about mice and keyboards. Just a recap from 2016. The most important question we want to answer is for the Fujitsu keyboard. For all the other keyboards, we were able to replay attack. We can talk about this later, what this implies. But interesting enough, there were keystroke injections on these keyboards. So even though you don't know the key, because this is all the keyboards market themselves as being secure and using AES encryption. And although we don't know the key, we were able to inject keys on the host that is using the keyboard without, knowing the actual key for most of the keyboard. But the Fujitsu keyboard used a different chip, and we were not able to, understand it back then. And for new research, we added, more keyboards and a lot of more wireless presenters because we want to understand them as well. So that we get a better understanding of what we do. There are basically 3 approaches to do this. First one is the hardware analysis for such a research project, because we don't have internal data sheets on what they do. So it's just buying the hardware on Amazon or something like this. And first step is hardware analysis, opening up the keyboards, the wireless presenters, look at the PCBs, look at the chips. Maybe there are markings on the chip. If you're lucky, you find a data sheet for the chip online. You learn more about this, about the chips there. And in some cases, you can even sniff the communication on the PCB and learn more about the chips. Of course, there's the radio-based approach to analyze the device. This is, like I said before, using the HackRF and software like Radio or Inspectrum to understand what they're actually sending over the air. Or you can use Crazy Radio and the NRF research firmware for NRF-based keyboards or presenters or mices. It makes it a lot easier because the coding is already handled by the chip. And for the firmware analysis, that's the third approach. We didn't do that much in this project, just because we didn't have the need to do it. Back in 2016, we actually did that, and it worked well on most keyboards. So most keyboards don't have the chips that are on there, not locked down. So you can just connect some wires to the chip, read out the firmware, and learn and understand how the keyboard is working. And in most cases, we were also able, of course, to extract the AES encryption keys, and then you can decrypt the traffic or emulate your own keyboard. So for the hardware analysis, this was what a typical presenter might look like, from Logitech at least in this case. And most of the time, that's why they work on all operating systems with most of the software for presenting, because the dongle just, emulates a USB keyboard. And when you press next slide or previous slides, in most cases, it is page up and page down, just what you're pressing. So this is why no additional driver is needed for that. And if you open the devices up, you can see a lot of different, ways the devices are designed. And they come in different form factors as well. So what you see here is this device here. It's like a ring shape, and I can use it in my finger and I can talk more freely. Really easy. In this case, you can maybe even see it. There are chip markings on that. You can search for the data sheet. It might be easy. Completely different presenter, completely different chip. So having different chips means, basically starting the research again, because with a different chip, or everything might be different for this presenter. Another presenter as well, different chip. This one is even trickier. As you can see, the chips are covered in epoxy. And you don't get any markings, and you don't know what chip is underneath there. For this chip, we were actually able to guess what chip is under there, because we soldered here some small wires between those chips. It's a 2-chip setup. The first chip is the microcontroller with all the firmware for pressing the keys and stuff on there. And the second chip is the transmitter, the RF transmitter chip. And if you sniff the communication in between, you might learn how the chip underneath the epoxy is working. Same for the Fujitsu keyboard. We had a look at it. Did the same approach. Because it was covered, we tried to read data with soldering wires on there. So after the first research, we could determine the chips that were in there. And as you can see, there are a lot of different chips. So there was a lot of work to do there. First of all, you try to find the datasheet, and in most cases, actually, we got lucky. So the chips for the NF24, the datasheet for the NF24 and for the Cypress chips, they're freely online available and used in some of these products, and you can learn a lot about these devices. In some other cases, like the Beacon RF chip, we got lucky as well. It is completely different vendors, but the chip is basically a clone of the NRF24 chip, so you can use a lot of the knowledge you gained before to, and you can apply it to the backend chips. And in some cases, like the HS304 chips, there was no datasheet online. We don't know. Mark Newlin reverse engineered part of the chips. That helped us a lot. But otherwise, no public information available. And for the radio-based analysis, there are tools like the Universal Radio Hacker for the software-defined radios. This is a tool that really helps you getting started to understand the packets that are, somewhere out there on the air. And you can easily decode them, and you can actually use this tool as well to resend package you recovered or craft your own package. So this is really helpful. But it's not that easy when talking about wireless analysis, because there are a lot of challenges. The first challenges, and this is even, one step is already done there. We have nothing. So there's just some signals in the air. So you need to guess a lot of things, or look at a lot of things, like what frequency, what modulation is it, frequency, amplitude, shift keying, or something like this. This is a decoded signal. You can see a digital signal here, but there's still a lot of to do. We're guessing these are still just ones and zeros. How do you get from these ones and zeros to eventually actually understand why a key A was pressed on the keyboard, for example? So the challenges are basically all this. We need to understand the signal modulation, the packet format, framing. We need to understand where packet length fields are, byte orders. Sometimes they're reversed. If there are checksums, how the checksums works. The payload field, of course, the most interesting. We want to understand where is the actual key A or key B that was pressed on the keyboard. And for some other challenges you need to have in mind is in the RF spectrum is frequency hopping, for example. Some of the devices do frequency hopping, so they change rapidly the frequency, and you have to follow them if you want to get the signal right. Or data whitening and data scrambling. We hadn't had that before, but in this research, some of the chips use data whitening and data scrambling. This is not encryption, but on the air, it's better for the receiver to understand what the sender was sending when there's a lot of changes between ones and zeros. It's just easier to understand for them. And for that case, some of the chips use data scrambling, and data scrambling is just XORing some more or less random string. It's hard-coded somewhere in the chip, XORing on the actual data to get a lot of changes. But we as researchers need that string, otherwise XORing some unknown string about some data is basically encryption. So we need to have that string in order to get reverse the data scrambling. The data structure for these packets are most of the time pretty similar. They're like preamble, sync word. There's that address, of course, because if your neighbor buys the same keyboard, you don't want when you press keys on the operating the neighbor's PC or the other way around. There are some control fields, the actual payload, and a checksum. This was true for most of the receivers. And if you looked at the data sheets and the ones and zeros in the air, you eventually come to something like this. So you understand what the preamble is. You can dissect the actual address that the chips are using, some more control fields, payload length fields, and of course, most important, the actual payload that is sent by the devices and the CRC checksum field. So this is an example for one of them, but they are similar in most cases. So let's talk about the actual attacks we can do. And there's a really old one and really obvious one. At least for us, it was obvious, because for all the keyboards, and that's why we have it here again, for all the presenters, it was true as well, because there are presenters out there. They have mouse emulation as well that you can show with your mouse pointer when you're presenting. And we noticed that the mouse, even even of the encrypted keyboard, the mouse communication is always unencrypted and unauthenticated. So if we understand the protocol correctly, we can just spoof a mouse. Well, it's not that interesting, but let me quickly show you. Some demonstration. This was in 2016 as well. We just wrote a proof of concept to show people that maybe it's also interesting to, or maybe good to encrypt your mouse as well. Because of when we control the mouse, well, of course, with a mouse, it's not that easy to attack in PC, but every PC, at least on Windows, has an on-screen keyboard, and you can just search for the on-screen keyboard, of course. Well, maybe you will not find it by the first try, but maybe you find it by the second or by fourth. Doesn't matter. It comes on top. And if you never used it before, it's always 100 pixel from the top and 100 pixel from the left. So there's some conclusions where we can find it even without a back channel, and that makes it, well, more or less reliable. And, well, it's a funny way to show this mic. Of course, the screen must be unlocked, but it actually worked. And it's actually also resolution independent, because mouse movements are resolution independent. So there are some things that make this attack work better and some make it harder. This is why that's really slow, because the curve of mouse acceleration is really hard to understand. But even when you do small steps, you can actually, well, this is just a PowerShell download and execute payload of some ransomware or something like this. It takes a time, but point proven, it is possible. So apart from spoofing mouse movements, what can we do else? Of course, there are replay attacks. This is most basically just recording the signals we have captured in the air, for example, with a software-defined radio, and just replay the signal. And for our research, we found out that all the presenters we had were actually vulnerable for that. So if somebody is here presenting and clicking next slide, and you record it with a device, you don't have a clue about the actual format that the presenter is using. Doesn't matter. Just save the data into a file and send it with the software-defined radio later, and it will go to the next slide or to the previous slide. Just as a side note, this was true for most of the keyboards as well we analyzed so far. So what you can do actually with a keyboard is, when you come into the office at the morning and somebody is recording, well, if you boot up your PC, the first thing you will enter is the username and the password. And if you go to a coffee break and lock the screen, you can just resend the signal out and it will unlock the PC. So this works there. We have a YouTube video showing this if you're interested in it. Pretty simple. But for wireless presenters, well, it's not that interesting. Of course, I can, well, mess up the person trying to present in front of you, but we can actually take over the PC just with a page up and page down button. So more interesting are the keystroke injection attacks. So what if we can enter some keystrokes here? And as we found out, the data for the presenters are still unencrypted and unauthenticated. So by understanding the whole packet format, we were able to understand where are the actual page up and page down button. And if we can craft the same package with some other device and just switch out the page up and page down button with, let's say, the A key or the B key or the C key, we were interested, will the emulated USB keyboard in the dongle accept these keys, although the presenter doesn't have that keys, in order to attack the PC where the dongle is connected to? And we found out that 2 of them actually had some kind of whitelisting, not accepting the keys that easily, but most of them were just vulnerable for these keystroke injection attacks. And I will try this live. Like every live demo, I will hope it works. As I said, the devices nowadays use 2.4 gigahertz signals, and I think the room here is pretty much crowded with Wi-Fi and Bluetooth and what on. So, pardon me if it does not work. So I will exploit these ring presenter here. This is we showed on some other logic presenters that it works, but this was part of the newer research, and this device was vulnerable as well. I will use the crazy radio dongle for that because it has a compatible chip to the chip here in the receiver, and there's a special firmware on it that lets me send whatever I want. And this is just an attacker PC, not really interesting to see. Just a command line tool I can start here that will find this device, emulate the actual presenter here, and not just pressing page up and down, but other keys. And let's see if it works. And as you can see, it just opened the command prompt and typed something in just as a proof of concept. Of course, you can change it to whatever you want, download and execute. Again, so this worked pretty easily. Of course, it was not encrypted, it was not authenticated, but this is true for most of the presenters. So I guess it's interesting if you present and if you want to be secure. This is why the presenter from the conference is still lying here and I'm not using it. So you can't only, because the tools are already online, so you can get them on GitHub and try it out at home. Maybe not at your neighbor, at least in Germany. This is not allowed by law. For the keystroke injection attacks, for the presenters was pretty easy, but what's about the Fujitsu keyboard? We didn't understand back then. And back then, when we're talking about this, we analyzed the 3 other keyboards down there, and we found at that time a cryptographic issue in the way they use the AES counter mode. So they actually use encryption, they actually use AES, but they just don't use it right, and therefore we were able to inject keys, although we don't know the actual AES encryption key. But this did not work for the Fujitsu keyboard. There's a different chip on that keyboard, and the way it was programmed, it was just not vulnerable for this kind of attack. But as we have a closer look, so this is the Fujitsu keyboard, as you can see there. It's a 2-chip setup as well. You can also sniff the communication again between. And when we had a closer look into the transmitter chip, so the chips are from Cypress, the keyboard is from Fujitsu. And what most chip manufacturers do to some kind of showcase their chip, they providing you example code or something like this. And Cypress was had some website up there, and you can search for it. And there was some example, some software development kit where you can check that it was especially for that chip or for these chip series. And within the chip series, there was example code for this is how you can do a basic keyboard. And this basic keyboard, of course, it's just example code, it's an unencrypted keyboard, but you can use that. And it turns out that the Fujitsu people actually most likely used that example code with the unencrypted keyboard and added encryption to it. We were not able to decrypt it or to inject encrypted packages, but our assumption was maybe if they used the unencrypted keyboard code and added encryption, did they remove the unencrypted keyboard code after adding the encryption? And turns out they didn't. So instead of injecting encrypted package, we just send plain text package to the chip, and the chip processes the plain text packages as well. And we were able to gain keystroke injection here as well. So this chip uses data whitening, and this is rather hard. So we did the same like with the Crazy Radio. We bought a board that has the same chip like used in the keyboard. This is again some from some multicopter drone hobbyist remote control chip, but it has the same chip we want to use, and that's good enough for us. And it also on the back side, I have this chip here. I'm not sure if you can see it back there. On the back side, there's even a small microcontroller where you can program code to. So this is a standalone attack, even we don't need something. So we put the demo code on the controller here. On the other side, there are the transceiver chips. This device has 4 transceiver chips, but one of them is for the Fujitsu keyboard, and we program it just to send the unencrypted keystrokes. Let's try this in a live demo as well. it worked a lot of times, but I was presenting this live deck and at some point and did not work. Let's see if it works this time. So just connecting a battery over here. So the board has some power to run. And as you can see, well, not doing anything. It blinks a little bit here. Well, that's everything. You can even make it smaller if you want to. But works again. So keystroke injection on the keyboard that supposedly should be secure, AES encrypted, but they just forget to remove the unencrypted keyboard code from there. After we had a closer look at the LX 901, this is the one I just showed you, the keyboard. People asked us about the LX390 keyboard. And sure, well, fair enough. It advertised itself as a secure 2.4 technology keyboard, but not mentioning AES encryption somewhere. So was interesting for us to have a closer look. This is the datasheet or the product sheet before we had a closer look, and the other datasheet down there is the datasheet after we had a closer look. I know the font is really tiny, but you may spot the difference. So of course we, when we find security vulnerabilities, we do a responsible disclosure and tell the manufacturers, and they updated the keyboard. Actually, this keyboard is you can no longer buy it. They have better ones now with better encryption. Let's quickly have a closer look in that keyboard. It was an interesting journey because it was basically the lockdown chips. And just by sniffing the communication with a logic analyzer, you can get the sequence what the one microcontroller is telling the receiver chip. And on the receiver chip, we noticed a pattern we known before. And this is, well, when the device boots up, it configures the RF chip, like what data rate it should use, what channel it should use, stuff like this. And from that, we were able to reconstruct what chip must be under there. And we found out it must be an LT8900 based chip somewhere. But when we understand this and what the chip actually is, we can again build our own. Well, first of all, this is when we decoded the packet. Now that we understand what they talk about each other to each other and how they configured, we again can do the radio-based analysis, capture the package and decode the package to understand what is going on there. And of course, again, the important part is something like the payload here and the CRC checksum. And it turns out this chip uses data whitening, so the scrambling, we have to understand how this works. And even though the plain text is always the same, so it has no replay protection or something like this, the actual CRC, when we buy two different keyboards, you can see here the last part is the CRC is different. So we found out that the CRC is initialized with a device-specific byte. But first of all, the data scrambling, that was more easy because the data scrambling was the same on every keyboard. So by reversing the data scrambling for one keyboard, you can apply to just all other keyboards. You have to make a lookup table basically. And again, this is just a basic CRC, no message authentication code, no real security. So we can again spoof the keyboard. Just for the sake of completeness, you can brute force the CRC, how it's working, and you can see down here. There's a device-specific value. In this case, we have to initialize the CRC with this value. And if you want to, hack the keyboard of your neighbor, of course, you just sniff one packet and brute force the CRC. And if you're hitting the right CRC, you found your device-specific initialization value, and it will be used for all packets there. So, again, to recap, it has no protection against replay attack. It has no protection against, it has no real encryption, so sensitive data is not really protected there. And there's no data authenticity, so we can just spoof the device. So replay attacks, keystroke and key sniffing attacks are this time possible. And my colleague actually wrote that too. I'm not sure if it's already public, but it's just another proof of concept that you can actually, in this case, decode what the people typing on the keyboard. So if they type the password in, you are able on this secure keyboard to sniff the actual keystrokes that were pressed and recover the keyboard and the login credentials or whatever the email the person is typing. So conclusions: unencrypted and unauthenticated data communication. Of course, this allowed us all the spoofing and injection attacks. Missing code protection against replay attacks. Well, we can do replay. This is rather easy. And the cryptographic issues we saw, we can bypass some cryptographic things and inject keys. And in some cases, we even are able to decode the actual key strings there. So from the presenters, we had a closer look. Most of them are vulnerable to keystroke injection. Some of them had some sort of whitelisting them, a little bit better. And for some of them, mouse spoofing worked. This does not mean there's no mouse spoofing. These presenters just didn't have a mouse pointer in them. And as we were not the only ones researching the wireless presenters, I want to show you this from Mark Newland as well. He had a look at different presenters as well and came to the same conclusion. It's basically possible all the time to inject keystrokes. Sometimes limited. Some Logitech products that do not allow sending A, B, C, or D keys, but in some of the cases you can press the Alt key and the num block keys, and with Alt and num block you can type Unicode symbols on, at least on Windows, and again you have a full keyboard with that. And updating our 2016 research with the with the Fujitsu wireless input devices, as I showed you the keystroke injection, we were able to do this as well. So some recommendations: choose your wireless presenter input devices, maybe by looking at some table, or maybe we jump to the last point, maybe not at all if you really want to be secure. Of course, if you're in environments that demand high security, I would recommend not to use them at all. At some points, you can consider Bluetooth-based input devices. In most of the cases, they're more secure when they paired. During the pairing process, there are a lot of vulnerabilities, especially in the Bluetooth Low Energy devices, the old ones. If the attacker is near you while you are pairing the presenter with your laptop using Bluetooth Low Energy 4.0, like most of the presenters with Bluetooth or keyboards, you are able to extract the key as well and can inject code again. And for some of them, there are replacements or updates available. You can have a look into that, especially for Logitech products. But if in doubt, just use a wired one. And if you're interested in trying this at home, most of the software is online available. So Mark Newland's wireless presentation work is online and the tools are on GitHub. Marcus Mengs, who did the research on the Logitech products, his tools are online as well. You can try them. And our fork of Mark Newland's presentation clickers repository, where we added our keyboards and the presenters we analyzed, is also available online. You can have a closer look. And if we have just some short anecdotes, funny because the AS encrypted keyboard by Cherry, we had 2016 a closer look. You can no longer buy it as B Unlimited AES, but they built a new one. It's the B Unlimited 3.0, really new and shiny, but it has still the same cryptographic weakness we found in 2016. So they fixed the security issue just by rebranding it. So before there was, this is a secure keyboard. Now when you buy it, there's no more secure printed on the keyboard, and a keyboard without printing secure in it, well, there is no security issue if the keyboard wasn't secure in the first place. And another interesting thing to keep in mind when I say, look at the table and you say, okay, I buy the August presenter or something because this was the best in this research. This is the Logitech R400. We bought it from Amazon, like at 3 different points of time and clicking on different shops. And this is what we got. 3 different versions of the R400. All completely different hardware. And I'm not sure if the first one we analyzed, and this is for sure, attackable with keystroke injection. The other ones we haven't had a closer look. We contacted Logitech. If the others are just cheap Chinese clones because the logo was slightly different and the presenter was lighter and something like this. And Logitech refused to answer because, well, the parts on the presenters are internally and are under disclosure, so they won't tell us if they are real products or not. But if you search online, Logitech is saying that if you have a Logitech product, the USB vendor ID, for USB product, there's a vendor ID, should be the one from Logitech. And for the first one, this is true. For the other 2, the vendor IDs from some Chinese chip manufacturer. So not really Logitech. Not sure. Maybe they changed the production just because it was cheaper. But so even if you buy the most secure one, maybe you don't get a secure one because if you don't open it up, you don't know. So this is what they said. Translating to something like the parts are copyright protected information, so won't tell us. And one more thing, we're not finished yet with that research. There are other devices out there like the barcode scanners also that you can get. Basically, they're just keyboards as well. We're having a closer look into them as well. Maybe there will more attacks on wireless input devices. And the slides will be online. You can have a look at all the references and check out all the stuff. And with that, I'm finished. Thank you. And if you have some questions, I'm ready to get them.
Thank you for this interesting talk. And, well, German precision, the timing is spot on. So we have time for questions.
Yeah.
So for the first keyboard, you are saying that it can process both encrypted and unencrypted message. Yep. How does it make a difference? Like when you receive the message, how you can tell that it's...
Actually, we don't know. This was one of the chips that has the firmware locked on the chip, so we can't read out what they actually programmed on the chip. But the data structure is just different from an unencrypted and encrypted package. And I guess somewhere they're parsing it different when the data structure is different when coming in from the transceiver dongle.
Okay, thank you.
There's no flag like saying this is encrypted or non-encrypted. It's just a different data format.
Some more questions? Okay, I do have a question. Yeah. It's more of a political question, actually, because I'm looking at all this. It seems like a lot of work, and it must be time-consuming.
Yeah, it is.
And they don't seem to be prototypes in any case, meaning that these are products that are being sold in the market. So who finances this research? So what is the I mean, of course, it's fun, and I understand the motivation for that. Yeah. But do you guys approach the companies for bounty hunting or things like that, or?
And in some cases, so it started. The first research in 2016 started actually as a customer project because a bank was want to use encrypted keyboards, wireless keyboards, and they asked us, "Is one of these 3 encrypted keyboards secure?" And they say, well, you have 1 or 2 weeks to analyze them. And we thought, okay, we give it a shot, but in 1 or 2 weeks, we can't actually tell much. But we saw enough to say, well, this is pretty interesting and we want to learn more about it. And at that point, it was just self-investment, basically 50% from the company. And, well, to be fair, the other 50% are free time doing it somewhere in the evening. And then again and again and again. And after a while we had the first devices, reported the first devices, some of the actual manufacturers of these devices cooperated with us for newer products, and we tested the products and give them some feedback on what they can improve on the products.
Okay, thank you very much. Are there any other questions? Yeah.
So for the presenters, can you actually see which presenter it is from just sniffing, or if you inject So because if you are in the audience right now, someone could inject right now, right?
Yeah. Okay, I have removed the dongles, but I guess for the other presenters, for the other people presenting here, this might be true. Yes, in most cases you can. So the data structures are that different. If you know them, you can see what chip must be, at least if it's one of the common ones, and most of the time they're pretty common. Even in most of the cases, you can just use this device because the chip on here is compatible with a lot of devices and is also compatible for the backend chips because the backend chips are just clones. You can just use this device also for sniffing. This device is capable of sniffing. Thanks to, I think, Travis Goodspeed is here somewhere. Because there's some tricks in the chip you can use for sniffing, and if you see what is there in the air, you probably can guess the rest from that. If the presenter is a presenter we had never take a look before, I'm not sure if you can say it that way, but if it's known, you can distinct them from each other.
Did you try to use the FCC ID to find other details about the device or not?
Yeah. We did from time to time. So the FCC ID is an ID if you sell a product in America. Every radio-based product must have an unique ID that must be printed on the product. And it was interesting enough, at least for the Logitech presenters, there was the same FCC ID on all of them, although we get them with different chips. And another interesting story was actually from the Cherry keyboard. We searched for the FCC ID and the FCC ID wasn't there. They did a typo in the FCC ID they printed on the product, so you're not able to find them. But for the first research, it's from time to time, it really helps. But we buy them anyway, open them up anyway, so we get the internal pictures from the FCC ID report by ourselves. So possible as well.
So we have time for more questions. Okay, so thank you very much again. Let me